The cosmos holds a secret from its very first moments. What if the first things to appear after the Big Bang were not stars, but black holes? We are talking about primordial black holes, some of the most bizarre and compelling mysteries in all of science. By the end of this journey, you will understand 25 radical theories that could completely reshape our story of dark matter, the birth of galaxies, and the fate of the universe itself. We will explore how these ancient objects might be hiding in our own solar system, how they could solve a glaring cosmic lithium problem, and whether they are echoes from a universe that existed before our own. What is your biggest question about the beginning of everything? The leading contender for their identity is not a particle, but a shadow. Theory number 1 proposes primordial black holes could be the universe's missing dark matter. For decades, scientists have known that galaxies hold together with a gravitational glue we cannot see, a substance we call dark matter. The search for what makes it up has focused on exotic, undiscovered particles. But what if the answer is not something tiny, but something dense and ancient, scattered everywhere? Primordial black holes, born in the chaos of the first second, fit the profile perfectly. They are dark, they do not emit light, and their gravity would be exactly what shapes galaxies and bends the path of starlight. They are what cosmologists call a cold dark matter candidate, meaning they would have moved slowly in the early universe, allowing structures like galaxies to form. The idea is beautifully simple. Instead of inventing a new type of particle physics, we look to gravity's own most extreme creation, forged in the furnace of the beginning. But if they are everywhere, why have not we found them? This is where the detective work gets fascinating. Astronomers have searched for these hidden black holes by watching for a phenomenon called microlensing. If a primordial black hole drifts between us and a distant star, its gravity will act like a lens, bending the star's light and causing it to briefly brighten. Massive surveys like OGLE and EROS have spent years staring at millions of stars, looking for these telltale flashes. They have not found enough to say that all dark matter is made of black holes the size of stars or planets. But they have not ruled out smaller ones. This is where the plot thickens. The current hot topic is a specific mass window, black holes with the mass of a large asteroid, perhaps as heavy as a small mountain, but crushed into a space smaller than an atom. These would be too small and too numerous to detect easily with current microlensing, leaving a glaring hole in our observations, a perfect hiding place for the universe's secret mass. So the possibility remains that dark matter is not a sea of invisible particles, but a cosmic graveyard of unimaginably dense relics, each a fossil from the first moment of time, silently holding the galaxies together. That search for hidden mass leads us from the distant edges of the galaxy to our own cosmic backyard. Theory number 2 proposes that a primordial black hole could be the mysterious planet 9. For years, astronomers have tracked a group of small, icy objects orbiting far beyond Neptune. Their paths are peculiar, clustered and tilted in a way that suggests the gravitational pull of something large and unseen. The leading explanation has been a rogue planet, perhaps 5 to 10 times the mass of Earth, lurking in the frozen darkness, but there is a compelling alternative. What if the culprit is not a planet at all, but a black hole forged in the Big Bang, one with the same mass as that hypothetical planet? The scale is mind-bending. A primordial black hole with 5 Earth masses would be crushed into a sphere only about 9 centimeters across, roughly the size of a grapefruit. It would be utterly black, emitting no light, a ghost of pure gravity drifting through the outer solar system. This tiny, dark object could perfectly explain the strange orbital dance of those distant icy bodies. Its gravitational signature would be identical to a planet of the same mass. The difference is in how we might find it. Searching for a faint, cold planet at the edge of our solar system is incredibly difficult. Searching for a black hole of that size seems impossible. But scientists have devised clever ways to look. If this primordial black hole is out there, it is not completely isolated. The sparse gas and dust of the outer solar system, and even particles of dark matter theorized to fill our galaxy, would occasionally fall into it. As this material spirals inward, it would heat up and produce tiny bursts of radiation, brief flares in X-rays or gamma rays that our telescopes could, in principle, detect. Furthermore, some models suggest that a primordial black hole might be surrounded by a dense halo of dark matter particles, and if those particles annihilate each other, they could produce a faint but steady glow of gamma radiation. We would be looking for a needle in a cosmic haystack, a single, faint, moving point of light against an infinite backdrop. Projects like the Legacy Survey of Space and Time at the Vera C. Rubin Observatory could scan the skies with such precision that they might catch this dark wanderer by the way it occasionally bends the light of a background star, a microlensing event happening right here in our own solar neighborhood. The hunt is on. We may be on the verge of discovering that one of the most mysterious objects in our own celestial family is not a planet but a primordial fossil, a silent keeper of ancient secrets orbiting just beyond our sight. The sheer scale of these cosmic giants presents a timeline problem of its own. At the heart of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole, an entity weighing millions or even billions of times our sun's mass. The puzzle is not just their size, but their age. Astronomers have spotted fully grown, supermassive black holes powering brilliant quasars when the universe was less than 1 billion years old, a mere infant by cosmic standards. How did something so monstrous form so quickly? The standard story is that they grew from the collapsed cores of the first massive stars, stellar black holes that then spent eons consuming gas and merging with others. But the clock seems too short. There is simply not enough time in the early universe for a star-sized black hole to eat its way to supermassive status. This is where theory number 3 offers a radical shortcut. What if the seeds for these giants were not born from stars at all, but were already waiting in the cosmic nursery? Primordial black holes created with intermediate masses hundreds or thousands of times that of our Sun could have been present from day one. They would have been the ultimate head start, massive seeds planted directly into the dense gas clouds of the young cosmos. With such a large initial mass, their gravitational pull was immediately ferocious. They would have begun sucking in the surrounding material at a phenomenal rate, a process called accretion, growing exponentially faster than any star-born black hole ever could. This model elegantly explains those impossibly early, impossibly bright quasars. They are not anomalies, but the natural outcome of a universe that began with ready-made heavyweights. The contrast is stark. In the stellar model, a black hole starts small and must race against time. In the primordial seed model, it starts the race halfway to the finish line, with a gravitational advantage that lets it win. Observations from the James Webb Space Telescope are now peering back to this epoch of cosmic dawn, searching for the faint glows of these growing seeds. They are looking not for the brilliant quasars themselves, but for their quieter, younger predecessors, black holes in the act of becoming supermassive. Finding them would be a monumental clue, evidence that the architects of the largest structures in existence were not born from the death of stars, but from the violent birth of reality itself. This origin story for black holes rewrites the first chapter of cosmic history. To understand theory number 4, we must travel back to the most fleeting moment imaginable, a fraction of a second so small it defies comprehension, when the universe underwent a process called inflation. Picture the cosmos not as an expanding ball of fire, but as a field of energy, a sort of cosmic fabric stretched taut. In this state, the rules of quantum mechanics reign supreme. At the tiniest scales, this fabric is not smooth, but fizzing with random fluctuations, little pockets of slightly higher or lower energy that pop in and out of existence. Normally, these quantum jitters are insignificant and vanish instantly. But during inflation, something extraordinary happened. The universe expanded faster than the speed of light, stretching space itself so violently that those tiny quantum ripples were frozen in place and blown up to astronomical sizes. A microscopic bump in the energy field became a macroscopic mountain in the density of the early cosmos. This is the crucial moment where the field was denser, more matter and energy were deposited as the universe cooled. Some of these over-dense regions, these cosmic mountains born from quantum seeds, would have been so extreme that their own gravity overwhelmed everything else. They did not wait for stars to form and die. Instead, they collapsed directly, catastrophically, into black holes the moment the conditions were right. Their birth certificate was signed by quantum uncertainty and stamped by hyper-fast expansion. To visualize this, think of a calm pond. The natural ripples on its surface are like quantum fluctuations. Now imagine the pond suddenly, impossibly, expanding to the size of an ocean in an instant. Those tiny ripples are now gigantic, rolling waves, frozen into the new, vast landscape. Some of those waves are so steep they crest and break, collapsing under their own weight. That breaking wave is the direct formation of a primordial black hole. This theory elegantly links the weirdest rules of the very small with the most dramatic objects of the very large. It suggests that the distribution of black holes across the cosmos is not random, but a direct map of those initial quantum tremors stretched across the sky. The pattern of where these ancient black holes ended up could, in principle, tell us about the physics of inflation itself, offering a way to test theories about the universe's first split second that no particle accelerator on Earth could ever reach. This quantum origin story forces us to confront one of the deepest mysteries in physics. Why does anything exist at all? In the fiery forge of the Big Bang, energy should have condensed into equal amounts of matter and its mirror opposite, antimatter. When matter and antimatter meet, they annihilate in a flash of pure energy. If the universe had been perfectly balanced, every particle should have found its opposite, and everything would have vanished into radiation, leaving behind a cosmos of empty light. Yet here we are, in a universe filled with galaxies, stars, and planets, all made of matter. Something tipped the scales, creating a tiny, 1 in a billion excess of matter over antimatter. This is the puzzle of baryon asymmetry, and theory number 5 offers a wild and elegant solution, placing primordial black holes at the heart of the story. The key lies in a process theorized by Stephen Hawking. Black holes are not completely black. Due to quantum effects at their event horizons, they slowly evaporate, emitting a faint glow of particles now called Hawking radiation. For a stellar or supermassive black hole, this process is unimaginably slow. But for a very small primordial black hole with a mass less than a small mountain, evaporation would have been rapid and spectacular, a final burst of energy in the early universe. Crucially, the physics of this evaporation might not be neutral. Some theories suggest that the extreme conditions and complex geometry of a tiny, evaporating black hole could violate a fundamental symmetry known as baryon number. In simple terms, baryon number is a kind of accounting system for matter. Protons and neutrons, the building blocks of atoms, have a baryon number of +1. Their antimatter counterparts have -1. In our everyday world, this number is conserved. It always adds up the same. But inside the quantum maelstrom of an evaporating black hole, that rule book might be torn up. The black hole could, in its final moments, emit just a little more matter than antimatter. Now, picture the early cosmos swarming with countless tiny primordial black holes, each one a ticking quantum bomb. As the universe cools, these black holes reach the end of their lives and explode in a cascade of Hawking radiation. If each explosion produces even a minuscule excess of protons over antiprotons, and if there were enough of these black holes, the cumulative effect could be staggering. They could have flooded the young universe with the raw material for everything we see, seeding it with the matter that would later form the first atoms. The timing is critical. For this to work, these particular black holes needed to evaporate completely after the initial matter-antimatter annihilations had already mostly finished, but before the epoch of Big Bang nucleosynthesis, when the first light elements like hydrogen and helium formed. This narrow window points to black holes with a very specific mass, perhaps around 1 billion metric tons, which is roughly the mass of a large mountain squeezed into a space smaller than a single proton. Their lifetimes would have been just a fraction of a second of cosmic time, but in that fleeting moment, they could have performed the universe's most important magic trick, conjuring substance from near symmetry. It is a breathtaking idea. The very objects we think of as the ultimate destroyers might, in their death throes, have been the creators of all we hold dear. The atoms in your body, the air you breathe, the ground beneath your feet, might ultimately be the ashes of ancient, evaporating black holes, the final gift from the first shadows of creation. That creative power of evaporating black holes points toward another, more violent cosmic signature. Theory 6 suggests primordial black holes could be the source of the universe's most energetic and mysterious radio flashes. Fast radio bursts are exactly what they sound like, brilliant blasts of radio waves that arrive from deep space, lasting only milliseconds but packing more energy than our sun emits in 80 years. Their origin is one of the great puzzles in modern astronomy. Among the many proposed explanations, from colliding neutron stars to alien megastructures, lies a fascinating possibility tied to our ancient black holes. One scenario involves a cosmic collision. Imagine a primordial black hole, perhaps the size of a city but with the mass of a planet, on a journey through the galaxy. Its path takes it directly through a neutron star, the ultra-dense corpse of a dead sun. As the black hole punches through the neutron star's incredibly rigid crust, it would send powerful seismic waves rippling through the star, a starquake. This sudden, catastrophic cracking could realign the star's immensely powerful magnetic field, releasing a colossal torrent of energy in the form of a radio burst. The timescale fits, the energy fits, and it would explain why some bursts seem to repeat, while others are one-off events, a single, fatal encounter for the neutron star. An even more dramatic idea focuses on the final moments of the smallest primordial black holes. As we discussed, a tiny black hole evaporates through Hawking radiation, and this process accelerates until it ends in a spectacular explosion. That final burst would not just be a puff of particles, it would be a gamma-ray flash of unimaginable intensity. Some theorists propose that as this flash slams into the surrounding gas and dust of the interstellar medium, it could generate a powerful shockwave, which in turn produces the coherent radio emission we detect as a fast radio burst. This would be a death cry echoing across billions of light years, a one-time only event marking the end of a black hole that had survived since the beginning of time. The challenge, as always, is evidence. While the energy and duration of these bursts align with what we might expect from such extreme events, no observation has yet definitively linked a fast radio burst to a specific location where a primordial black hole collision or evaporation could have occurred. It remains a compelling, elegant idea on the theoretical shelf, waiting for that one perfect piece of data, a radio flash with a telltale signature that points unmistakably to an ancient darkness meeting its end. The explosive death of a tiny black hole is one kind of violence, but their birth could have been even more cataclysmic. Theory 7 takes us to a moment of cosmic chaos, where primordial black holes were forged in the collisions of universe-altering bubbles. This idea stems from a concept called a first-order phase transition. We see phase transitions every day like water turning to ice, but in the early universe, a phase transition could have been unimaginably violent. Picture the fabric of reality itself shifting from one state to another, like water finally reaching its boiling point and turning to steam. According to some models of cosmic inflation, the end of that hyper-fast expansion was not a smooth settling down. Instead, the universe cooled into its current stable state in a patchy, uneven way. Bubbles of this new, true vacuum reality spontaneously formed in the seething, high-energy false vacuum of the inflating cosmos. Each bubble expanded at nearly the speed of light. Now, imagine countless such bubbles forming and growing in that primordial soup. They are not gentle. They are walls of fundamental force ripping through the unstable space around them. Eventually, these bubbles collide. When two of these incredibly energetic walls smash together, the collision is not a quiet merger. It is a titanic release of energy concentrated into a razor-thin region. The forces involved are beyond stellar. These collisions can create regions of space so incredibly dense, so warped, that they immediately pinch off under their own gravity, collapsing directly into black holes. In this scenario, primordial black holes are not born from gentle density ripples, but from the shrapnel of a universe tearing itself apart and reassembling into a new form. They are the cosmic scars left by the violent end of inflation, littering the newborn cosmos with dark matter potentially from the very first instant. The scale of these black holes would be set by the physics of the bubble walls, potentially creating them in a very specific mass range, offering a unique fingerprint for astronomers to search for. It is a dramatic origin story, one where the first structures were not gentle gatherings of gas, but the thunderclaps of reality settling into the rules we know today. Those violent collisions of cosmic bubbles might have seeded the universe with black holes of a very specific size, a size that has since shown up in our detectors. Theory 8 proposes that the binary black hole mergers detected by LIGO and Virgo are not the remains of dead stars but primordial black holes. When the first gravitational wave signal hit Earth in 2015, it announced the merger of two black holes, each about 30 times the mass of our Sun. This was a surprise. Stellar evolution models struggled to explain how massive stars could leave behind black holes this heavy, especially in pairs. There is a predicted mass gap between the largest neutron stars and the smallest black holes from stellar collapse, and many of LIGO detections land squarely in a range that makes astrophysicists pause. Primordial black holes offer a clean solution. They are not born from stars, so they do not have to obey the rules of stellar death. The chaotic conditions of the early universe could have easily produced black holes in the 30 to 50 solar mass range, perfectly matching the most common signals from LIGO catalog. The question then becomes, how did these ancient black holes find each other to merge? In the vast emptiness of space, a chance encounter between two lone black holes is extraordinarily unlikely. But primordial black holes have a unique advantage. They would not have been scattered randomly. According to their formation models, they would have been born in clusters, dense groups of these dark objects gravitationally bound from the very beginning. Within these clusters, close encounters are common. Two black holes could become gravitationally bound, forming a binary pair that slowly loses energy through gravitational waves over billions of years, spiraling closer and closer until they finally collide in an event we can now detect. This clustering property is a key prediction. If LIGO black holes are primordial, we should see a statistical pattern in their mergers, hints that they came from dense environments rather than isolated stellar systems. The data is still coming in, but each new chirp from the cosmos adds another point on the graph. A primordial origin would elegantly solve the mass gap puzzle and explain why we are seeing so many of these heavy mergers. It suggests that the ripples in space-time we are now measuring are not the death throes of recent stars, but the final dance of relics that have been circling each other since the dawn of time. Their merger a long-delayed echo of the universe's first second. The echoes of those ancient collisions might have subtly warped the very fabric of the cosmos, leaving a discrepancy in our most fundamental measurements. At the heart of modern cosmology lies a growing crisis called the Hubble tension. In simple terms, we have two primary ways to measure how fast the universe is expanding right now, a number called the Hubble constant. One method uses the cosmic microwave background, the afterglow of the Big Bang, as a snapshot of the infant universe. By studying its intricate patterns, we can extrapolate forward to calculate today's expansion rate. The other method uses a cosmic distance ladder, carefully measuring the brightness of nearby stars and supernova to gauge the expansion directly. Both methods are incredibly precise, but they stubbornly disagree. The universe appears to be expanding faster today, according to the local measurements, than the pristine early light says it should be. This is not a small error. It is a significant gap that has withstood years of rechecking, suggesting our standard model of cosmology might be missing a crucial ingredient. Theory 9 proposes that primordial black holes could be that missing piece, not through their gravity today, but through their influence in the first few 100,000 years after the Big Bang. The key lies in the cosmic microwave background and the imprint left by sound waves traveling through the early universe's hot plasma. The scale of these frozen sound waves, called the sound horizon, is a cosmic ruler etched into the microwave sky. Our calculation of the Hubble constant from the cosmic microwave background depends critically on the length of this ruler. Primordial black holes, if they formed early enough and in sufficient numbers, could have changed that ruler's length. Here is how it might work. If a significant population of primordial black holes formed before the universe was about 1 day old, they would have been massive, compact objects moving through a sea of radiation and ordinary matter. Their gravity would have created tiny wakes in this primordial soup, subtly affecting how the sound waves propagated. Think of trying to measure the speed of sound in a calm lake versus one with scattered, heavy rocks just below the surface. The waves would travel differently, arriving at the shore at slightly different times. In the cosmic sense, this means the sound horizon measured in the cosmic microwave background would be a slightly different size than if no black holes were present. If we mistakenly assume no black holes were there when we read the cosmic microwave background data, we would get the wrong answer for the Hubble constant. By including the gravitational effects of these early black holes, the cosmic microwave background could be made to predict a higher expansion rate for today's universe, potentially bringing it into line with what we measure locally. The balance is incredibly delicate. The number and mass of these primordial black holes must be just right to tweak the early universe's sound waves without contradicting other constraints, like the successful predictions for the formation of light elements. It is a high-stakes cosmic adjustment, where a shadowy population from the dawn of time might be quietly correcting one of the most pressing puzzles in modern astronomy, a subtle fingerprint of ancient darkness on our brightest map of the beginning. The subtle influence of primordial black holes on the early universe is a testament to their deep connection with fundamental physics. This connection leads us to Theory 10, which elegantly ties together two of cosmology's greatest puzzles. It proposes that primordial black holes could be born from the collapse of action stars, linking the world of hypothetical particles directly to the formation of cosmic shadows. Actions are a leading candidate for dark matter, conceived to solve a problem in particle physics concerning the strong nuclear force. Unlike the weakly interacting massive particles, or WIMP, that many have searched for, actions would be incredibly light, behaving less like discrete particles and more like a pervasive, wave-like field filling the cosmos. Under the right conditions, this field could clump together under its own gravity, forming vast, diffuse objects called action stars or oscillatons. Picture not a ball of fiery gas, but a gigantic, fuzzy quantum cloud, trillions of kilometers across yet holding only a few times the mass of our Sun. It would be a ghostly, self-gravitating wave oscillating in a delicate balance. The stability of such an object is precarious. If an action star grows too massive, or if it encounters a dense region of ordinary matter, this balance can shatter. The entire structure, this immense quantum wave, can undergo a sudden and catastrophic gravitational collapse. There is no supernova, no stellar core to compress. Instead, the entire fuzzy ball of wave-like dark matter collapses directly in on itself, its quantum nature overwhelmed by the sheer force of its own gravity. In a final, decisive moment, the oscillating field condenses into a point of infinite density, birthing a black hole. The transition is mind-bending, a fundamental shift from a spread-out quantum object to the ultimate classical singularity. This theory is profoundly elegant because it does not require the extreme densities of the Big Bang's first instance. Instead, it uses a dark matter candidate that we already have theoretical reasons to believe in, and shows how it can naturally evolve over cosmic time into the black holes we are trying to explain. It creates a bridge between the quantum realm of particle physics and the gravitational realm of astrophysics, suggesting that the dark matter halos enveloping galaxies might not be smooth and featureless, but could contain these ticking time bombs, ancient action stars on the verge of collapsing into new, primordial black holes long after the universe's birth. The link between black holes and cosmic explosions brings us to one of the most violent phenomena in the universe. Theory 11 suggests primordial black holes could be the hidden engines behind gamma-ray bursts, the most luminous flashes of energy we have ever witnessed. These bursts come in two distinct flavors, long and short, each with a potential connection to these ancient objects. For a long gamma-ray burst, which can last from 2 seconds to several minutes, picture a primordial black hole on a collision course with a massive, rapidly spinning star. As the black hole, perhaps with the mass of a planet or even a star, plummets into the stellar interior, it does not simply punch a hole. It begins a catastrophic disruption from the inside out. The black hole's immense gravity tears at the star's core, swirling material into a furious, ultra-hot accretion disk while simultaneously funneling twin jets of particles at nearly the speed of light out through the star's poles. These jets, drilling their way out of the stellar envelope, are the source of the brilliant gamma-ray flash we see. The entire star is effectively eaten from within, its core replaced by a voracious dark seed that triggers a supernova-like explosion with a focused, jet-powered fury. This scenario could explain certain unusual long bursts where the accompanying supernova seems oddly faint or missing, as if the star's demise was orchestrated by an internal saboteur rather than its own fuel exhaustion. The story for short gamma-ray bursts, which last less than 2 seconds, is even more direct. These are already strongly linked to the mergers of neutron stars, events that also produce gravitational waves. But a primordial black hole could step in as a perfect stand-in. Imagine the final moments of a binary pair of primordial black holes, locked in a death spiral for billions of years. Their merger would be a spectacular event, rippling space-time and, in some models, potentially surrounded by a faint shroud of accreted gas. As the two black holes become one, the violent shaking of space-time could energize this material, resulting in a brief, intense flash of gamma rays. An even more likely scenario involves a primordial black hole merging with a neutron star. This would be a truly apocalyptic encounter. The black hole, far denser and more compact, would begin stripping material from the neutron star the moment they touch. The neutron star, unable to withstand the tidal forces, would be shredded in seconds, its material forming a brief, incredibly hot disk around the black hole before being swallowed. The energy released in this process, both from the accretion and from the possible launch of jets, would easily power a short, brilliant burst of gamma radiation. The challenge for astronomers is the signature. A merger between two primordial black holes might look very similar in gravitational waves to a merger of stellar black holes, and the gamma-ray flash from a black hole neutron-star merger might be indistinguishable from one caused by two neutron stars colliding. The telltale clue would lie in the masses involved. If we detect a gravitational wave signal from an object in the so-called mass gap, or from a merger with a total mass that seems impossibly high for stellar remnants in that region of space, the primordial black hole theory gains compelling weight. These bursts of light, therefore, may not just be the death cries of stars, but the final, brilliant sparks from collisions between the universe's oldest and darkest relics. The hunt for the earliest cosmic signals has led to one of the most perplexing discoveries in recent memory. Theory 12 takes us to a mysterious dip in a radio signal from the cosmic dawn, a clue that primordial black holes might have been busy heating the infant universe. The story begins with the EDGES experiment, a simple but ambitious radio antenna in the remote Australian outback. Its goal was to listen for a specific whisper from a time when the universe was only a few 100 million years old, before the first stars and galaxies fully ignited. This whisper is the 21-centimeter line, a faint radio signal emitted by neutral hydrogen gas as its atoms change their spin state. By measuring the strength of this signal, astronomers can effectively take the temperature of the early cosmos. What EDGES heard or thought it heard sent shockwaves through cosmology. The data showed an absorption trough twice as deep as any standard model could predict. This meant the hydrogen gas at that epoch was much colder than expected, or the background radiation bathing it was much hotter. Either way, something was dramatically wrong with our picture of cosmic dawn. The universe seemed to have been chilled or illuminated by a mysterious new source of energy. This is where primordial black holes enter as a potential culprit. In the standard model, the first stars eventually heat the hydrogen gas, ending this absorption phase. But what if something else was heating the gas much earlier? A population of small primordial black holes drifting through the vast clouds of primordial hydrogen could have done exactly that. As these black holes moved, they would have pulled in hydrogen gas. While even a small black hole's event horizon is tiny, the gas falling toward it compresses and heats up, emitting soft X-rays and ultraviolet radiation long before the first stars could do so. This early bath of radiation would have excited the hydrogen gas, making it appear as if it was absorbing a stronger background signal, perfectly creating that anomalously deep trough in the 21-centimeter line. An alternative, even more exotic idea involves the radiation from the black holes themselves. If these primordial black holes were of a specific, small mass, they would have been evaporating via Hawking radiation right around this cosmic epoch. That evaporation would have flooded the universe with a diffuse glow of photons and particles, again providing an early source of heating and ionization. The timing is critical and incredibly fine-tuned, requiring a specific mass range for the black holes to be active at precisely the right moment to explain the EDGES data. The controversy is far from settled. Many scientists question the EDGES result itself, pointing to potential calibration errors or interference from our own galaxy. But if the signal is real, it points to physics beyond our standard models, and primordial black holes offer a compelling, if speculative, solution. The next chapter of this mystery will be written by a new generation of radio telescopes. Projects like the Square Kilometre Array, a vast network of antennas being built across South Africa and Australia, will have the sensitivity and resolution to map the 21-centimeter signal from cosmic dawn in exquisite detail. It will not just listen for a single dip, but create a three-dimensional map of the early universe's temperature. If primordial black holes were indeed the early universe's first heaters, their distribution should have created a specific patchy pattern in this map, a shadowy imprint of their presence. We are on the verge of either confirming a radical rewrite of the universe's first chapters or finally laying this deep cosmic chill to rest. The cosmic dawn's faint radio whispers point to structures forming in the universe's infancy, but what if the seeds for those structures were not just points but walls? Theory 13 ventures into a realm of pure geometry, where primordial black holes could have been forged from the collapse of cosmic domain walls. To grasp this, we must think of the early universe not as a smooth soup, but as a patchwork quilt of different phases. Picture the fundamental fields that govern reality cooling from a chaotic, high-energy state like water freezing into ice. But just as water can form ice crystals with different orientations, these cosmic fields could have settled into distinct, stable configurations or vacuum states in different regions of space. The boundary between two such regions is not a simple line. It is a cosmic domain wall, a two-dimensional sheet of immense energy density stretching across the cosmos. Think of it as a flaw in the fabric of spacetime itself, a vast, invisible membrane where the rules of the universe change from one side to the other. These walls are not static, they are under tremendous tension like a rubber sheet stretched to its limit. They possess mass and therefore gravity. Over time, the dynamics of the expanding universe would have caused these walls to bend, ripple, and intersect. In some scenarios, a closed loop of a domain wall, a gigantic, fluttering sheet folded back on itself, could form. This loop is unstable. Its own immense gravitational pull, concentrated in a finite area, can cause it to contract. As it shrinks, the energy density within the loop skyrockets. There is no force strong enough to stop the collapse. The wall contracts faster and faster, the curvature of spacetime within it becoming infinite, until the entire structure, a sheet of pure energy thinner than a proton but potentially light years across, pinches off into a singularity. It is a geometric birth where a flaw in the vacuum itself becomes a black hole. The masses produced could vary wildly, from asteroid size to far heavier than our Sun, depending on the size of the initial wall fragment. The final trigger for this collapse might be a quantum event. Even a stable-looking wall is subject to quantum tunneling, a random chance that allows it to suddenly transition to a lower energy state. This sudden decay would release the wall's pent-up energy in a cataclysmically localized burst, a perfect recipe for black hole formation. This theory connects the deepest principles of quantum field theory to astrophysical reality, suggesting that the first black holes might not have been born from matter at all, but from the topology of empty space, from the scars left behind when the universe chose its permanent shape. The geometric collapse of domain walls is a beautiful idea, but our search for primordial black holes often returns to the evidence of our own eyes, or rather, the evidence of bent starlight. Theory 14 brings us back to a real astronomical campaign that once held the spotlight, the hunt for MACHO. MACHO stands for Massive Astrophysical Compact Halo Object, a name that perfectly captures what astronomers were looking for in the 1990s and early 2000s. The goal was straightforward: to find the dark matter in our galaxy's halo by watching for its gravitational effects. Teams like the MACHO project and EROS set up shop, their telescopes trained not on distant galaxies but on our galactic neighbors, the Large and Small Magellanic Clouds. Night after night, they meticulously recorded the brightness of millions of stars in these satellite galaxies. Their hope was to catch a singular event, a star in the cloud briefly brightening because a dark, compact object in our own Milky Way's halo had drifted directly in front of it, its gravity acting as a temporary lens. This is gravitational microlensing, and for a while it seemed to work brilliantly. The surveys detected dozens of these events. The duration of each brightening told a story. A longer event suggested a heavier lensing object. The data revealed a tantalizing pattern. Many of the events pointed to objects with masses roughly between 1/2 and 1 times the mass of our Sun. This was the sweet spot for one particular candidate: primordial black holes of stellar mass. The interpretation was electrifying. It suggested that a significant portion, perhaps up to 20%, of our galaxy's dark matter halo could be made of these ancient black holes wandering invisibly between the stars. For a time, primordial black holes were not just a wild theory, they were a leading explanation supported by real, observed data. So what happened? Why did this promising lead fade from the forefront? The decline came from a combination of factors. First, the microlensing signal itself was complex. While some events perfectly matched the profile of a compact object, others were ambiguous. Could some have been caused by faint, ordinary stars or brown dwarfs within the Magellanic Clouds themselves, rather than dark objects in our halo? As statistical analyses improved, the initial estimates for the number of macho were revised downward. Second, and more profoundly, the rise of the cosmological model favoring cold dark matter particles shifted the entire paradigm. Particle dark matter offered a more elegant explanation for the large-scale structure of the universe, the intricate cosmic web of filaments and voids that seemed difficult to build from chunky black holes alone. The macho results, while intriguing, could not account for all the dark matter, and the particle hypothesis promised a single, universal solution. The microlensing interpretation for primordial black holes fell out of favor, relegated to a footnote in the dark matter saga. But a footnote is not a dismissal. The crucial point is this: the macho surveys were never disproven. They were simply overshadowed. The events they recorded are real, and a population of stellar mass primordial black holes remains one of the few viable explanations for them. They could easily account for that 20% or so of the galactic halo's dark mass, with the remainder being something else, perhaps actions or other particles. This idea has experienced a quiet renaissance, with the gravitational wave discoveries from LIGO revealing so many black holes in that very same mass range. The macho data looks newly relevant. Those flashes of light from the 90s might have been our first direct detection of the ancient black holes we are now hearing merge across the cosmos. They were not the entire dark matter story, but they could have been its most dramatic characters, hiding in plain sight all along, their presence revealed only by the fleeting brightening of a distant star. The microlensing searches left us with clues, not conclusions, but the fingerprints of primordial black holes might also be etched into the very elements that compose our world. Theory 15 tackles a stubborn mismatch in our cosmic recipe book, the baffling lithium problem. When we peer back to the first few minutes after the Big Bang, to an era called Big Bang nucleosynthesis, our equations perform a near miraculous feat. They predict with stunning accuracy the amounts of the lightest elements forged in that primordial furnace, the hydrogen and helium that make up nearly all the visible matter in the cosmos. Yet for one element, lithium-7, the predictions are catastrophically wrong. The universe today, when we measure the pristine lithium in the oldest stars, holds only about 1/3 of the amount our best models say should exist. Something in the early universe was destroying lithium almost as fast as it was made, and primordial black holes offer a compelling saboteur. The solution lies in the violent death of the smallest black holes. Picture the cosmos just minutes old, hot and dense with a soup of protons, neutrons, and newly minted nuclei. Swarming through this soup are countless low-mass primordial black holes, each one a ticking quantum clock. For black holes with masses around 1 billion metric tons, their lifetime would be measured in mere minutes, perfectly coinciding with the window of Big Bang nucleosynthesis. As these black holes reach the end of their lives, they do not fade quietly. They explode in a final, furious burst of Hawking radiation, flooding their immediate surroundings with an intense shower of high-energy particles, protons, and neutrons moving at nearly the speed of light. This is where nuclear alchemy happens. When a high-energy proton ejected from a dying black hole slams into a newly formed nucleus, it can shatter it in a process called spallation. Think of it as a cosmic game of billiards played with atomic fragments. A high-speed proton smashing into a nucleus of beryllium-7, a fragile isotope that is the main precursor to lithium-7, can blast it apart. The specific reaction is devastating. A proton plus beryllium-7 yields 2 helium-4 nuclei. In one instant, the building block for lithium is utterly destroyed, converted into stable, inert helium. Alternatively, these high-energy particles could also break apart other larger nuclei like boron or carbon that formed in trace amounts, further altering the delicate chemical balance. The timing and the mechanism are exquisitely precise. If these evaporating black holes were too numerous or their explosions too energetic, they would have disrupted the entire nucleosynthesis process, ruining our perfect predictions for hydrogen and helium. But if they existed in just the right abundance, with just the right mass to evaporate during that critical lithium-forming window, their particle bombardment would act like a subtle filter. They would selectively deplete the fragile lithium-7 without significantly disturbing the robust yields of hydrogen and helium-4. It is a cosmic tuning of the most delicate kind, where the ashes of evaporating black holes subtly prune the elemental garden of the early universe. This idea transforms the lithium discrepancy from a frustrating error into a potential signal. The missing lithium is not a mistake in our physics, but a clue. It could be the direct aftermath of a population of tiny, quantum black holes breathing their last in the infant cosmos, their final particles erasing a specific line from the periodic table. If this theory holds, then the abundance of lithium in the oldest stars is not just a measurement of nuclear physics, but a fossil record of quantum gravity in action, a lasting echo from the instant the first shadows in the universe vanished in a blaze of light. The destruction of lithium points to a violent, particle-filled early cosmos, but the seeds of those black holes might have come from an even more exotic source. Theory 16 ventures into the abstract mathematics of fundamental physics, where primordial black holes are born from the fragmentation of a cosmic field. To understand this, we must move beyond particles of matter and into the realm of fields, the underlying fabric of reality. In the first moments, the universe may have been permeated by what physicists call complex scalar fields. Think of this not as a thing you can touch, but as a kind of energy landscape, a vast, undulating terrain of potential that filled all of space. In the hot, dense conditions of the Big Bang, this field was smooth and uniform like a perfectly calm sea. But as the universe expanded and cooled, this calm was an illusion. Instabilities began to ripple through the field. It is akin to a sheet of ice forming on a pond. The surface looks solid, but internal stresses can cause it to suddenly crack and buckle into a mosaic of frozen plates. For the scalar field, these instabilities caused it to fragment. It broke apart into dense, localized lumps of concentrated field energy. These lumps are known in some theories as Q-balls, not physical balls, but stable, soliton-like configurations where the field is wound up in a specific, self-sustaining way. They are knots of pure field energy holding themselves together against the tendency to dissipate. Now, gravity enters the picture. Each of these Q-balls possesses mass simply by virtue of the energy it contains. If a Q-ball is massive enough, its own self-gravity becomes significant. The knot of energy begins to pull itself inward. There is no need for ordinary matter to be present. The field itself, under its own gravitational attraction, can undergo a direct collapse. The Q-ball contracts, its energy density soaring to unimaginable levels until it crosses the threshold where not even light can escape. A black hole is born not from gas or dust or colliding bubbles, but from a knot in the fabric of a fundamental field. This theory is profoundly elegant because it is deeply tied to speculative but compelling extensions of our known physics like supersymmetry. In such models, scalar fields are not just mathematical curiosities, they are expected players in the early universe drama. The formation of Q-balls and their subsequent collapse into black holes becomes a natural, even inevitable consequence. It forges a direct and beautiful bridge between the most abstract equations of particle theory and the most tangible, gravitational objects in the cosmos. The black holes we might detect today with gravitational waves or microlensing could, in this view, be the fossilized remnants of these primordial field defects. their existence a direct testament to physics operating at energies far beyond anything our particle colliders can ever reach. They would be cosmic fossils of a hidden layer of reality, made not of stuff but of twisted space-time itself. The universe is constantly bombarding Earth with atomic shrapnel moving at nearly the speed of light. These cosmic rays, mostly protons and atomic nuclei, carry energies that dwarf anything our most powerful particle accelerators can produce. At the very highest end of this spectrum, beyond a petaelectron volt, lies a profound mystery. What natural engine in the cosmos can possibly hurl a single proton with the kinetic energy of a well-thrown baseball? Theory 17 proposes that primordial black holes could be these cosmic p-vatrons. The name itself is a clue, a portmanteau of petaelectron volt and accelerator. We know the sources for lower energy cosmic rays like supernova remnants, but the PV frontier demands something more extreme, more compact and more efficient. An evaporating primordial black hole fits the profile perfectly. Recall that a small black hole, through Hawking radiation, does not just emit a gentle glow. In its final, explosive second of existence, it becomes a furnace of ultra-high-energy particles. The temperature of a black hole is inversely related to its mass, so a tiny, mountain-mass black hole in its death throes would be incredibly hot, emitting a burst of particles, including protons, electrons, and gamma rays, at energies that can easily reach the petaelectron volt scale and beyond. This is not a steady beam, but a final, catastrophic shotgun blast into the surrounding space. Any particle caught in that blast would be catapulted to unimaginable speeds. But there is another, more sustained mechanism. Imagine a primordial black hole not quite ready to evaporate, drifting through a dense molecular cloud in our galaxy. Even a small black hole possesses immense gravity for its size. As it plows through the cloud, it would pull in gas, forming a miniature, ultra-hot accretion disk. The magnetic fields tangled in this swirling maelstrom could act as a natural particle accelerator, similar to processes around supermassive black holes but on a far more compact and intense scale. Charged particles caught in these magnetic whirlwinds could be whipped around and ejected in narrow jets, reaching petaelectron volt energies. This would create a steady, point-like source of ultra-high-energy cosmic rays. The challenge, as always, is finding the evidence. A single, random cosmic ray hitting our atmosphere tells us little about its origin. The key is correlation. If primordial black holes are the source, they are likely not isolated. They would exist in clusters as predicted by their formation models. A cluster of these objects, all either evaporating or accreting matter, would not only produce cosmic rays but also a correlated shower of other signals. The same violent processes that accelerate protons would also produce high-energy gamma rays and neutrinos, ghostly particles that travel in straight lines from their source. This gives astronomers a multi-messenger hunting strategy. If we detect a burst of petaelectron volt neutrinos from a specific, seemingly empty patch of sky, and then find a matching flash of gamma rays from the same location, it could point directly to a hidden cluster of primordial black holes. It would be a cosmic signature with three distinct components, a trifecta of extreme physics. Observatories like the Ice Cube Neutrino Observatory at the South Pole and gamma-ray telescopes like the High-Altitude Water Cherenkov Observatory are now mapping the high-energy sky with this exact goal. They are searching for these coincident flashes, the potential smoking gun that would reveal ancient black holes not by their gravity, but by the furious particle storms they generate. Each unexplained PV event is a clue, a possible tracer bullet shot from a dark, ancient engine that has been running since the beginning of time. The particle storms from dying black holes are one kind of violence, but a far slower and more insidious destruction may be unfolding inside the ancient stars of our galaxy. Theory 18 proposes that a captured primordial black hole could be the hidden trigger for a white dwarf explosion, rewriting the story of one of cosmology's most important tools. A white dwarf is the Earth-sized, ultra-dense core of a sun-like star that has run out of fuel. It is a sphere of carbon and oxygen, supported not by nuclear fusion, but by a quantum mechanical pressure, a last line of defense against its own immense gravity. These stellar cinders are famously stable, destined to cool slowly into dark cosmic diamonds over trillions of years, unless, of course, something disrupts that delicate balance. The standard model for a Type Ia supernova, the brilliant explosion of a white dwarf, involves it stealing material from a companion star until it reaches a critical mass limit and detonates in a thermonuclear runaway. Yet astronomers have observed peculiar supernovae that don't quite fit this picture, events that are either too faint, too bright, or lack a visible companion star. A primordial black hole offers a compelling alternative villain. Imagine a solar system forming from a primordial cloud of gas and dust, a cloud that also contains a wandering, asteroid-mass black hole from the dawn of time. As the star forms and lives its life, this dark passenger could be captured into a wide orbit. When the star eventually dies and puffs off its outer layers to become a white dwarf, the black hole's orbit would decay, slowly spiraling inward through a process called dynamical friction. Over billions of years, it would sink through the degenerate matter of the white dwarf like a stone through thick syrup, leaving a faint, hot trail in its wake. Eventually, it reaches the very center. Now the quiet cinder has a parasite at its heart. The black hole, though tiny, begins to slowly accrete material from the white dwarf's core. This process does two things. First, it injects heat, warming the core from the inside. Second, and more crucially, it gradually removes the supporting mass from the very center of the star. This can destabilize the entire structure. In one scenario, the heating could ignite a runaway fusion reaction that does not begin at the center, as in the standard model, but propagates in a strange, asymmetric way, potentially explaining those unusual, off-kilter supernovae. In another, quieter scenario, the black hole acts as a slow drain. It consumes the white dwarf from the inside out, not with a bang, but with a whimper. The star's mass decreases until it can no longer support itself as a white dwarf. Instead of exploding, it undergoes a gentle gravitational collapse, compactifying further into a neutron star, all without a brilliant supernova flash. This would leave behind a neutron star with no supernova remnant and no obvious origin story, a ghost in the stellar graveyard. The timescales are cosmic patience personified. The entire process, from capture to final consumption or explosion, could take longer than the current age of the universe, meaning many of these dark partnerships may still be in their early stages, ticking quietly inside faint white dwarfs across the Milky Way. This theory challenges our understanding of stellar death, suggesting that some of the universe's most dramatic fireworks, or its most silent transformations, might be orchestrated by a microscopic speck of ancient darkness, a fossil that found a home and decided to eat its way out. The quiet consumption of a white dwarf points to a slow, gravitational feast, but the birth of a primordial black hole can be a sudden, seismic event in the fabric of reality itself. Theory 19 takes us to a pivotal cosmic moment when the fundamental forces of nature underwent a radical shift. In the first microseconds after the Big Bang, the universe was not filled with atoms or even atomic nuclei. It was a seething, opaque soup of quarks and gluons, the most basic building blocks of matter, all swimming freely in a state known as a quark-gluon plasma. It was a world without protons or neutrons, a realm of pure, unconfined energy. Then, as the cosmos expanded and cooled, it crossed a critical threshold. This is the QCD phase transition, where the strong nuclear force, quantum chromodynamics, suddenly took hold. The free quarks and gluons were forced to bind together, condensing into the first protons and neutrons, much like water vapor condensing into droplets. In our standard textbooks, this transition is smooth, a crossover. but many physicists suspect it could have been violent, a first-order phase transition. Think of it not as mist gently settling, but as supercooled water suddenly and explosively freezing. In a first-order transition, the new phase, hadronic matter, would not form uniformly. Bubbles of this new reality would spontaneously nucleate in the sea of quark-gluon plasma and expand at nearly light speed. The collision of these expanding bubble walls would have been sites of immense energy concentration. The universe would have been filled with a cacophony of shockwaves, a cosmic thunder as reality changed state. These collisions create regions of extraordinary density, perfect gravitational seeds. If the density in these colliding walls was high enough, they would have immediately collapsed into black holes. The scale is set by the physics of the transition itself. The size of the bubbles and the energy released determine the mass of the resulting black holes. Calculations point to a fascinatingly specific range, masses comparable to planets like Earth or even larger. This is not a random guess, it is a prediction that emerges directly from the equations of particle physics. A planet-mass primordial black hole is a profoundly interesting object. It is too large to have evaporated by now through Hawking radiation, so it would be a stable, permanent relic. It is also in a sweet spot for detection. For microlensing surveys, a planet-mass black hole drifting in front of a star would cause a brightening event lasting for weeks or even months. A long, smooth curve of light that modern time-domain astronomy is perfectly suited to catch. Dynamically, these objects would be heavy enough to subtly tug on star clusters and the delicate structures of stellar streams in our galaxy's halo, leaving gravitational fingerprints we are just learning to read. They could be the macho that earlier surveys hinted at, or the elusive planet 9 stirring up the outer solar system. This theory ties the existence of these dark wanderers directly to a fundamental event in particle physics, offering a potential observational test for something that happened in the first microseconds of time. If we find a population of planet-mass black holes, we may be looking at more than just dark matter. We could be witnessing the frozen aftermath of the moment the universe learned how to build an atom. The violent shift from quark soup to atomic matter was a particle accelerator of cosmic proportions, but the smallest black holes might be even more prolific particle producers. Theory 20 casts primordial black holes as the universe's ultimate neutrino factories. When we think of a black hole evaporating, we often picture it emitting a faint glow of light, a thermal bath of photons. But Hawking radiation is far more democratic. A truly evaporating black hole emits every fundamental particle species that can exist at its temperature, from photons and electrons to quarks and, crucially, neutrinos. These ghostly particles, which barely interact with normal matter, would stream out in vast numbers, especially during the black hole's final, explosive second. For a tiny primordial black hole with a mass around 1 billion metric tons, its temperature in those last moments would be astronomical, high enough to produce neutrinos with significant energy. This turns a dying black hole into a brilliant, fleeting point source of these elusive particles. If such an event happened relatively nearby, within our galaxy or even our local cosmic neighborhood, the neutrino burst could be intense enough to register in our most sensitive detectors. Observatories like IceCube, buried deep in the Antarctic ice, or Super Kamiok, and a giant water tank in Japan, are designed to catch the rare flashes of light produced when a neutrino does, against all odds, interact with an atom of water or ice. A nearby primordial black hole death would create a very specific signature, a sudden spike of neutrino events, all pointing back to a single, tiny region of space, all arriving within a fraction of a second. The numbers are compelling. Calculations suggest the final second of a mountain mass black hole could release a neutrino flux with a total energy comparable to a supernova, but packed into a volume of space smaller than an atom and a timescale 1 billion times shorter. It would be a needle-sharp, unimaginably bright flash in the neutrino sky, The challenge, of course, is the background. Our universe is not quiet in neutrinos. The Sun produces a steady stream of them, distant supernovae create bursts, and even the diffuse glow from all the cosmic rays hitting interstellar gas creates a persistent neutrino fog. Distinguishing a single, point-like flash from a primordial black hole from this cacophony is like trying to hear a specific firecracker pop in the middle of a roaring stadium. The key is in the energy profile and the directionality. A black hole evaporation would produce neutrinos across a very broad spectrum, with a significant fraction at extremely high energies, where the astrophysical background is much thinner. Furthermore, if multiple neutrinos from the same microsecond event hit the detector from precisely the same direction in the sky, that coincidence would be a screaming red flag. No known astrophysical process, aside from perhaps a neutron-star merger, creates such a brief, energetic, and point-like neutrino signal. So far, our detectors have not seen anything that definitively matches this profile. But they are listening. Every unexplained high-energy neutrino cluster, every strange microsecond burst that seems to come from nowhere is scrutinized. The hunt is a testament to patience, requiring us to monitor the entire sky, waiting for a ghostly whisper that signals the end of a universe-spanning journey, a final sigh from a darkness that has lasted since the beginning. Deep in the heart of our galaxy, a brilliant mystery glows in invisible light. The center of the Milky Way is a crowded, chaotic place, home to a supermassive black hole and millions of stars packed into a dense nuclear cluster. When astronomers pointed the Fermi Gamma Ray Space Telescope at this region, they expected to see a lot of activity. What they found was more than they could easily explain. A diffuse, persistent fog of gamma-ray radiation, the highest energy form of light, seems to emanate from the galactic core in a spherical halo. This is the galactic center excess, and its source has been a puzzle for over a decade. The radiation is too smooth and too widespread to come from known astrophysical objects like pulsars or the remnants of supernova. Something else is bathing the core in this energetic glow. One of the leading explanations has been the annihilation of dark matter particles. In this model, when two hypothetical weakly interacting massive particles, or WIMP, collide, they would annihilate each other in a flash, producing gamma rays among other things. The density of dark matter is thought to be highest at the galactic center, so that is where the signal should be strongest. It is an elegant idea that could solve two puzzles at once: the identity of dark matter and the source of this gamma-ray fog. But there is a compelling challenger to this particle story. Theory 21 suggests the glow might not come from particles at all, but from the collective fury of ancient black holes. Imagine a vast, invisible swarm of planet-mass primordial black holes drawn by gravity into a dense cloud at the Milky Way's core. These are not the evaporating kind, but stable, asteroid or planet-sized dark relics. They would be invisible on their own, but space is not empty. The galactic center is filled with a thin, hot gas of ionized particles and a theorized haze of dark matter particles. As these primordial black holes drift through this environment, two things could happen. First, they could directly accrete some of this tenuous gas. Even a tiny trickle of material spiraling into a black hole heats up and can emit radiation, including gamma rays. A single black hole would produce an undetectably faint whisper, but millions of them, concentrated in the same region, could create a collective hum that adds up to the observed excess. Second, and perhaps more powerfully, the black holes themselves could be surrounded by ultra-dense mini-halos of dark matter particles. The immense gravity of each tiny black hole would pull in and concentrate the surrounding dark matter, creating a spike in density around it. In these dense spikes, the rate of dark matter particle collisions and annihilations would be dramatically enhanced. Each black hole becomes a bright lighthouse of annihilation radiation, its signal amplified far beyond what would occur in empty space. The combined glow from millions of these lighthouses could perfectly mimic the smooth, spherical gamma-ray haze we see. This sets up a fascinating detective story for next-generation telescopes. How do we tell if the signal is from annihilating particles or annihilating particles supercharged by primordial black holes? The key is in the details of the map. A smooth sea of annihilating dark matter particles would produce a very specific, symmetric pattern of light. A swarm of black holes with dense dark matter halos would create a subtly different pattern. The distribution might be slightly clumpier, as the black holes themselves would cluster in ways that pure dark matter particles would not. Furthermore, if the black holes are accreting ordinary gas, there might be correlated signals at other wavelengths, like X-rays or even faint radio waves. Future instruments like the proposed Compton Spectrometer and Imager, or COSI satellite, will map the galactic center's gamma rays with unprecedented precision and spectral detail. They will look for these tiny statistical wrinkles in the glow, the fingerprints of discrete sources hidden within the fog. The implications are profound. If the excess is traced to primordial black holes, it means we have not only found a major component of dark matter, but we have also located a vast, ancient colony of them, a fossil graveyard at the heart of our home galaxy, illuminating itself through its own dark influence. The final moments of inflation were not a gentle settling, but a cosmic thunderclap. Theory 22 takes us into the turbulent epoch of preheating, a chaotic aftermath where the universe reheated itself in a frenzy of resonant energy transfer. Picture the inflattened field, the engine that drove the universe's hyper-fast expansion, finally running out of steam. It did not simply switch off. Like a released spring, it began to oscillate wildly around its lowest energy state. This oscillation was not a gentle sway, it was a violent, coherent vibration that shook the very fabric of space-time. Crucially, the inflattened field was coupled to other quantum fields, the ones that would later give rise to all the matter and radiation we know. As it oscillated, it pumped enormous amounts of energy into these other fields through a process called parametric resonance. Think of it like a master violinist playing a note so pure and powerful that it causes every other instrument in the orchestra to vibrate in perfect, explosive sympathy. In the cosmos, this resonance created explosive bursts of particle production. Regions of space became overstuffed with energy, growing not smoothly but in sharp, jagged spikes. The universe during preheating was not a uniform soup, it was a seething, turbulent sea of colossal density contrasts. In some patches, the energy density skyrocketed to hundreds of times the average, while neighboring regions were left relatively empty. These were not the gentle quantum ripples stretched by inflation, but giant, nonlinear mountains of density forged in a post-inflationary firestorm. Gravity wasted no time. Any region where the density crossed a critical threshold, where the pull of its own mass overwhelmed the outward pressure of the hot radiation, would have undergone immediate gravitational collapse. There was no need to wait for gas to cool or stars to form. The universe, in its frenzied state of preheating, was already pregnant with black holes. The scale of this process is breathtaking. Because the density perturbations were so large and nonlinear, black holes could form across a wide spectrum of masses simultaneously. One calculation might yield a black hole the mass of a planet, while another, just a few patches away, might collapse into something as heavy as a star. This provides a natural, almost inevitable formation channel within many popular models of inflation. It is a compelling idea because it ties the formation of primordial black holes directly to the dynamics of the inflattened field's decay, a period we must account for in any complete inflationary story. The black holes become a predicted byproduct, a fossil record of the universe's violent transition from exponential expansion to the hot, dense plasma of the Big Bang. Their mass distribution would carry the specific signature of that resonant dance, a fingerprint of the frequencies at which the inflattened field shook reality. Finding a population of primordial black holes with a particular spread of masses could, therefore, tell us not just about gravity, but about the orchestra of quantum fields that played the universe into existence. The cosmic hum from countless black hole mergers is not just a theoretical prediction, it is a signal we may already be hearing. A population of primordial black holes, constantly pairing off and colliding across the breadth of cosmic history, would not just produce individual chirps. Their collective din would create a permanent, low-frequency rumble in the fabric of space-time, a stochastic gravitational wave background. Imagine standing in a forest during a heavy rain. You can hear the distinct plop of individual drops hitting leaves, but beneath that is the constant, soothing roar of billions of impacts merging into one sound. That roar is the gravitational wave background from primordial black holes. It is not a signal from one place or one time, but the accumulated echo of every merger that has ever happened, a fossilized soundscape of the universe's dark past. This hum is incredibly faint, a distortion in space-time far smaller than an atomic nucleus, but it is there, permeating everything. For years, scientists have been listening for it with a natural cosmic tool, pulsars. These rapidly spinning neutron stars act as universe-spanning metronomes, beaming radio pulses with extraordinary regularity. By monitoring an array of these pulsars across our galaxy, projects like NanoGrav, the European Pulsar Timing Array, and others can detect the subtle, correlated shifts in their ticking caused by a passing gravitational wave background. It is like sensing a gentle breeze by watching how it makes every blade of grass in a field sway in the same slow rhythm. Recently, these collaborations announced tantalizing evidence. They have detected a common signal across dozens of pulsars, a low-frequency hum that could be the first hints of this background. The leading explanation is the combined rumble from merging supermassive black holes in the centers of distant galaxies. But primordial black holes are a compelling and perhaps even more exciting alternative. If the mergers we see with LIGO are from ancient black holes, then their countless ancestors, merging throughout the cosmos over billions of years, would contribute their own chorus to this hum. The character of the sound would be different. The frequency and amplitude of the background depend on the masses of the black holes and how often they merge. A universe filled with primordial black holes of a certain mass would sing a very specific tune. Current pulsar timing data already places limits, ruling out models where these ancient black holes make up all of the dark matter if they are too heavy and merge too often. But the real revolution is just ahead. The next generation of dedicated space-based observatories will turn this faint hum into a symphony we can analyze note by note. The Laser Interferometer Space Antenna, or LISA, scheduled for the 2034, will be a trio of satellites flying in a giant triangle, sensitive to gravitational waves at much lower frequencies than LIGO can detect. It will listen for the mergers of black holes with masses from a few hundred to several million times that of our Sun, perfectly poised to hear the primordial black holes that could have seeded today's giants. Later, ground-based titans like the Einstein Telescope and Cosmic Explorer, with sensitivities far beyond current detectors, will catch the mergers of smaller primordial black holes with incredible volume. Together, these instruments will not just listen for a hum, they will dissect it. They will measure its strength across a wide range of frequencies, creating a spectral fingerprint. That fingerprint will be compared against detailed predictions from countless primordial black hole formation models. Does the background's strength match what we would expect if dark matter were made of asteroid mass black holes? Does its frequency spectrum show the telltale peak expected from black holes born in a first-order phase transition? The data will act like a cosmic sieve, ruling out vast swaths of theoretical possibility, potentially narrowing the hunt to a single triumphant scenario. Or it could reveal a hum that only primordial black holes can explain, a direct transmission from the universe's first second, finally audible after 13.8 billion years. The gravitational hum from ancient mergers might have orchestrated the first structures in the cosmos. Theory 24 proposes that primordial black holes did not just seed supermassive giants, they may have built the universe's first stellar cities. In the standard story of cosmic dawn, the first galaxies assembled slowly. Tiny density ripples from the Big Bang grew under gravity's patient pull, gathering dark matter and gas until pockets were dense enough to ignite the first stars, which then grouped into small pioneer galaxies. It is a gradual, bottom-up process, but the universe's oldest, smallest galaxies, the ultra-faint dwarfs that orbit our Milky Way, present a curious challenge. They are ancient, pristine, and incredibly dim, often holding only a few thousand stars. Their existence so early in cosmic time is puzzling, as if they formed in a hurry before they had a chance to gather more material. A population of primordial black holes offers a compelling reason for that rush. Imagine the young cosmos, still dark and filled with vast clouds of primordial hydrogen and helium. Drifting through these clouds are not just invisible particles, but compact, heavy anchors, clusters of primordial black holes with masses ranging from asteroids to stars. These clusters are not passive. Their collective gravity creates deep, localized wells in the fabric of space, places where the surrounding gas feels a much stronger pull than from smooth, dark matter alone. A gas cloud that might have taken 100 million years to collapse under its own weight could be dragged down into these pre-existing gravitational pits in a fraction of the time. The process is like sowing a field with heavy stones. Rainwater does not form puddles randomly. It immediately pools in the depressions around each stone. In the cosmic context, the primordial black hole clusters are the stones, and the primordial gas is the water, funneling rapidly into their gravitational basins. This triggers star formation prematurely and efficiently, creating a small, dense burst of stellar activity. The resulting galaxy would be tiny, faint, and old, exactly matching the properties of the ultra-faint dwarfs we see today. Crucially, these galaxies would form around the black hole clusters, meaning their dark matter halos would have an unusual, cuspy density profile, centrally concentrated in a way that pure particle dark matter struggles to explain. Cosmological simulations that include these heavy seeds show this exact effect. When researchers run virtual universes with a sprinkling of primordial black hole clusters, the first star-forming structures appear earlier and are more numerous than in simulations with only smooth dark matter. The galaxies that form are also more resilient. The violent feedback from the first supernova, which can blow gas away and stifle further star formation, has a harder time evacuating the deep gravitational well anchored by the black holes. This allows for multiple, quick bursts of star formation, again matching the complex stellar populations found in some ancient dwarfs. This theory elegantly links the largest scales of cosmology to the smallest fossils in our galactic backyard. Those faint, wispy galaxies orbiting the Milky Way might not be failed fragments, but the universe's first successful experiments, built not from the ground up, but from the inside out, with ancient black holes as their hidden foundations. Their dim light is a beacon pointing directly to the heavy seeds that guided their birth, a ghostly testimony to a time when darkness built the first homes for stars. The faintest galaxies might be built on ancient foundations, but the ultimate origin of those foundations could lie beyond our own reality. Our final theory, number 25, ventures into the most speculative and breathtaking territory of all. It proposes that some primordial black holes are not from our universe at all. They are cosmic immigrants, time capsules from other universes. This idea emerges from the edges of cosmology, from models of a multiverse or a cyclic cosmos. Picture not a single Big Bang, but an endless cycle of universes being born, expanding, and dying, or an infinite froth of bubble universes constantly budding off from an eternal inflationary background. In such a grand tapestry, what happens to the most resilient structures when one universe ends? a supermassive black hole or even a stellar mass one is arguably the most durable object in existence. Not even the end of a universe in some models can completely erase it, as one cosmic cycle contracts in a hypothetical big crunch or undergoes a dramatic bounce. All ordinary matter is annihilated, scrambled into its fundamental constituents. But a black hole, a knot of pure space-time curvature, might survive that transition. Its event horizon, the point of no return, could act as a protective barrier, shielding its singular heart from the chaos of the cosmic reset. When the new universe bursts forth in its next Big Bang, this relic would emerge not as a product of the new cosmos's initial conditions, but as a foreign artifact, a primordial black hole with a history older than time itself. In the bubble universe version of the multiverse, the mechanism is slightly different. Our universe might be one bubble in a vast, ever-expanding cosmic foam. When new bubbles nucleate, they do so in a violent process. It is conceivable that the collision of bubble walls in this metacosmos could not only create black holes, but also catapult them into the newborn bubble universes. These black holes would then be present from the very first instant of that new universe's history, appearing to its inhabitants as primordial even though they were forged in the fires of apparent reality. The implications are staggering. Such an object would be a literal fossil from a previous iteration of existence. Studying it, if we ever could, would be like an archaeologist finding a perfectly preserved smartphone in a Neolithic dig site. Its properties might not align with anything our physics predicts could form in our universe's infancy. Its mass, its spin, even the quantum information locked beyond its event horizon, could carry signatures of an entirely different set of physical laws, a different value for fundamental constants, or a different history of stellar evolution. Finding a population of black holes with inexplicable masses or spins, ones that simply cannot be accounted for by any formation channel within our own cosmic story, would be powerful, if not definitive, evidence for this mind-bending idea. It would mean our cosmos is not a lonely, one-time event, but part of a vaster, perhaps eternal, sequence. The primordial black holes we have been hunting, the potential dark matter, the seeds of galaxies, the sources of mysterious radiation, could be more than just relics of our beginning. They could be messengers, the only tangible evidence that our universe is not alone, that we are living in the aftermath of another reality's death, building our stars and planets from the ashes and the enduring shadows of a world that came before. From dark matter and a hidden planet to the missing lithium and echoes from other realities, a single class of object ties these cosmic puzzles together. Primordial black holes are not just one theory among many. They are a master key, a single conceptual framework with the power to unlock a dozen of the universe's greatest mysteries. Their story connects the quantum jitters of the first microsecond to the gravitational waves we detect today, weaving through the formation of galaxies, the heating of the cosmic dawn, and the very elements that make up our world. They remind us that the most profound answers in cosmology might not require inventing entirely new physics, but rather recognizing the profound consequences of gravity's oldest tricks. The search is now entering its most decisive phase. Within the next decade, an arsenal of new instruments will turn speculation into data, the Vera C. Rubin Observatory will scan the entire sky with such depth and frequency that it could catch the subtle brightening of a distant star as a primordial black hole drifts by, or even spot the faint, moving pinprick of a planet mass relic in our own solar system. The Laser Interferometer Space Antenna will listen for the low-frequency hum of merging black holes from the dawn of time, while next-generation gravitational wave detectors on Earth will dissect the masses of every merger with exquisite precision. Space telescopes will map the high-energy sky, searching for the unique gamma-ray and X-ray signatures of accretion or evaporation, and pulsar timing arrays will continue to refine the gravitational wave background, listening for the specific tune sung by a cosmos filled with ancient dark relics. One by one, these experiments will close the windows of possibility, either finding the unmistakable fingerprint of primordial black holes or ruling out their existence across vast swaths of parameter space. We are on the verge of knowing whether these shadows from the beginning are a beautiful theoretical dream or a fundamental feature of our reality. Until then, the power lies in the idea itself, a testament to human curiosity's ability to take a single, strange possibility and follow its threads to the edges of understanding. Which of these 25 theories resonates most with you? Is it the elegant solution to dark matter, the dramatic death of a white dwarf from within, or the mind-bending possibility of relics from a previous universe? Let us know in the comments below and subscribe to join us as we unravel the next great mystery of space and time.